Today we are talking about alkynes. And the good news about alkynes, if you remember, the alkyne is the carbon-carbon triple bond. The reactions of the alkynes are almost the same as the reaction of alkenes. So even though we are learning 7 new reactions today, they are pretty much repeats of the alkene reactions, just with the CC triple bond, so the products are a little bit different. So let's take a look here at our beautiful alkynes. Okay, there's two types of alkynes. There are terminal alkynes, which are alkynes at the end of a molecule. And you know they're terminal because they have a hydrogen attached to them. So this is called terminal alkyne. And the other type of alkyne that you can have is the internal alkyne, which is having carbon on the left and right. And in this part of the class, we're going to be looking at 6 reactions of the pi bond. And we're also, this is kind of special, we're going to be looking at 1 reaction of the hydrogen that's attached to an alkyne. So that's specific to the terminal alkynes, but the 6 reactions of the pi bonds will be general for both the terminal and the internal alkynes. One thing that I know you guys already know about the alkynes that's pretty important is they have a bond angle of 180 degrees. They are linear because the carbons of the alkyne are sp hybridized, so their bond angle is 180 degrees. And I'll just mention that in general, internal and terminal alkynes behave the same. And that is that they do the same reactions. But I just thought I would distinguish the two possibilities in case you hear me sometimes say, take a look at that terminal alkyne. I'll be referring to the one at the end of the molecule with the hydrogen attached. Okay, let's get started with these reactions. Reaction 1 is actually kind of review. So I'll say review-ish, because I can say that. And it is deprotonation. And this is the one reaction that's specific to the terminal alkyne. So this is acid-base / deprotonation. And this reaction is specific to terminal alkynes because only terminal alkynes have that hydrogen attached that we can deprotonate. Okay, no problem at all. So if you remember the pKa of the alkyne, you probably remember it's relatively low. So if we have an alkyne, we can deprotonate it with a pretty strong base. The pKa is 25, which is actually relatively acidic compared to something like an alkene, which is 44, or an alkane, which is 50. So 25 is actually quite a bit more acidic than the other hydrocarbon protons. And the base that's typically used to deprotonate alkynes is something called sodium amide. It's NaNH2. Just like we saw that NaH was used to deprotonate alcohols, NaNH2 is what we'll use in this class to deprotonate alkynes. And all that happens is the negatively charged nitrogen grabs the proton from the alkyne and dumps a lone pair onto the carbon. And this produces the following substance. It's a CC triple bond with a negative charge and sodium counterion, just a spectator ion, plus NH3, which is the conjugate acid of our base, which has pKa of 38. So you can calculate the KEQ of this reaction and convince yourself that it is quite favorable. But really what we want to focus on is this guy here, which is called the sodium acetylide. A sodium acetylide is a deprotonated alkyne, and it is a useful nucleophile. Specifically, it is a carbon-based nucleophile, which is rare. Up until now, we've only seen two other carbon-based nucleophiles, sodium cyanide, NaCN. We've seen NaCN. And we've seen organometallics, like organolithiums or magnesium bromide. So we've only seen two other carbon-based nucleophiles, and I've just shown those in red. And now this is a third carbon-based nucleophile joining that family. It's the sodium acetylide. So let's see what the sodium acetylide can do. Let's use it in an SN2 reaction. So acetylides are superb nucleophiles. So they can do a variety of important reactions. Specifically, they can do SN2. Although you have to be careful, they are prone to doing E2, and the reason is that they have a pK of the conjugate acid of 25, so they are a good base. So you have to be careful that E2 is not going to outcompete. But generally speaking, they're very good nucleophiles. So if we took an alkyl halide like this ethyl bromide, and we treated it with a deprotonated alkyne, the deprotonated alkyne will do SN2 reaction, attack the alpha carbon, kicking out bromine as a leaving group. The product will be substitution, replacement of that leaving group with the alkyne to give the product shown. And interesting to note here, this is a reaction that's making a new carbon-carbon bond. And we know that that's very important to be able to make a new carbon-carbon bond. So there's a deprotonated alkyne doing an SN2 reaction on a primary alkyl halide. One thing to note about the alkyne that makes it kind of special is it's very directional. It looks like a bullet or a spear. So it is a very, very good nucleophile in SN2 because the spear shape gives it a low steric profile. So bullet shaped. Low bulkiness. And we know that bulkiness is bad for nucleophiles. In fact, we saw the terbutoxide, KOTBU, was too bulky to even do SN2. So this is kind of like the other end of that spectrum, because this is so unbulky, because it's so straight and bullet-like, that it's really fantastic for doing SN2. Okay, so the deprotonated alkynes, or acetylides, don't just do SN2. They can do some special reactions. For example, they can react with carbonyls, similar to a Grignard or organolithium reagent. So we can say it reacts with carbonyls. So if you take, say, for example, acetone, and you treat it with step 1, a deprotonated alkyne, the sodium acetylide, and step 2, H2O workup, it will behave exactly like an organometallic and add the alkyne to the acetone to create an alcohol. So we can watch the mechanism of that transformation if you like. It's pretty much exactly what you'd expect. Okay. The negatively charged alkyne attacks the carbonyl carbon, kicking electrons up onto oxygen. Gives us a tetrahedral intermediate with an O- charge. And then the last step, water workup. The negatively charged oxygen grabs a proton from water to give us that alcohol. So deprotonated alkynes can react with carbonyls. And because they can react with carbonyls, they can also react with epoxides, just like organometallics. And also, just like organometallics, they attack the less substituted side. There's no way to do this under acidic conditions, so they always attack the less substituted side. So if we have this epoxide here, and we treat it in step 1 with our deprotonated alkyne, our sodium acetylide, and step 2, we'll still need that water workup. The product will be addition to the less substituted side of the epoxide to give us beta substituted alcohol. That'll look like that. Let's take a look at the mechanism. You have your deprotonated alkyne. It attacks the less substituted side of the epoxide, kicks electrons up onto oxygen. That gives us our alkoxide. And then the last step, water acts as an acid to donate a proton to the O- in the workup step to give us an alcohol. So you can see that the deprotonated alkynes are very useful. So if you have a terminal alkyne, consider deprotonating it and reacting it in an SN2 reaction with a carbonyl or with an epoxide. All right, so that's the reaction of the hydrogen of a terminal alkyne, just deprotonating it. Now let's take a look at, I'm looking at this structure here and I didn't love the way that I drew this. Let me just redraw this structure a little bit nicer, my product. There we go. That looks better. So again, it's very easy to lose carbons, and that's kind of what I was not loving about my structure with alkynes because they are linear. So let's just count the carbons just to confirm. 1, 2, 3, 4, 5, 6. So in total, our product should have 6 carbons. 1, 2, 3, 4, 5, 6, which it does. So just always count the carbons just to make sure you didn't add or remove carbons when you use the alkyne. Okay, let's take a look at the other reactions of alkynes, and specifically these are reactions involving the pi bond of the alkyne. So this will lead us to reaction 2. Okay, and a lot of these are going to seem familiar. Reaction 2 is the addition of HX. Hey, wasn't that the first reaction we looked at for alkenes? Yes, it was. So let's take a look at example 1. If you take an alkyne, we just take this alkyne for example, and treat it with HBr, HX, and I'm going to say 1 equivalent. You'll see why that matters. Then the product is going to be adding the bromine, in this case with using HBr, to the more substituted side of the alkyne. In that case, it's going to be this side of the alkyne. This side has a hydrogen, so it's the less substituted side. This has no hydrogen, it's the more substituted side. So the product is going to be as follows. Just like that, adding bromine to the more substituted side of the alkyne. Let's take a look at the mechanism. The mechanism is exactly the same as what we saw with the alkenes. But that's been a while, so you may want to go back and refresh. The pi bond of the alkyne attacks the H, kicking electrons onto bromine as a leaving group. And that's going to create for us a carbocation. So the hydrogen goes onto the right and generates the carbocation at the more substituted position. This is Markovnikov's rule. Remember, Markovnikov's rule states the rich get richer. So the carbon with the most number of hydrogens gets the additional hydrogen, which is exactly what's happening here. And now the Br minus acts as a nucleophile and attacks the carbocation to give us the product shown. In terms of regiochemistry, it's Markovnikov, because the rich get richer. In terms of stereochemistry, there's no control. For example, the bromine, I drew it on the top, but it could have just as well have been on the bottom here where the phenyl is. They could have swapped positions. There's no control. You can see the carbocation's flat, so the bromine can either attack from the bottom or from the top. No stereo control. Meaning you're going to get mixtures of cis or trans, potentially. Mixtures of E or Z. Let's take a look at example 2. If we take this alkyne, which is internal, and we add HBr, 1 equivalent, the bromine doesn't really have any preference on where it's going to add. Either side is equally substituted, so Markovnikov's rule goes out the window, and we're going to get both stereoisomers. So we'll end up getting the cis product, looks like this, and we'll get the trans product. Okay, so no stereo control. In other words, we get a mixture of isomers. That's kind of what I was saying with the example above. All right, now I keep mentioning this 1 equivalence. Why is that? Well, imagine we use 2 equivalents. Well, first we're going to do the alkyne version of the reaction, then we'll have an alkene, and we'll do the alkene version of the reaction. So let's take a look at that. Okay, let's take phenylacetylene, common alkyne, and we'll treat it with HBr 2 equivalents. Okay, the first thing that's going to happen, it's going to add the bromine to the more substituted side and the hydrogen to the side that has the most hydrogens already. So we'll get that. And then it reacts with the HBr again. And if you remember that alkenes react with HBr, also Markovnikov, also no stereo control, to add H to the side with the most number of H's and a halogen to the side with the least number of H's. So we end up getting 2 bromines added to that carbon. The double bond now completely gone, and now there's a total of 3 hydrogens on the end here. So this is called a geminal dibromide. So just remember this fact. If you ever see 2 bromines on a single carbon, it always came from an alkyne. So just remember that. If you ever see 2 bromines or 2 chlorines on the same carbon, it must have come from an alkyne, because this is the only reaction that puts 2 halogens on the same carbon. It's called a geminal dibromide. And again, just to recap the way it works, first it does the alkyne reaction, then it does the alkene reaction from the previous lectures. Okay, that's reaction 2. Let's take a look at reaction 3. Reaction 3 is called complete hydrogenation. Again, it's another reaction we've seen before. It's a way to delete alkynes. So as an example, if we have this alkyne and we treat it with the conditions that we've seen before, hydrogen and palladium on carbon, the solvent is typically methanol or ethanol, the alkyne will be reduced to an alkane. And so we'll just get this, where we've added a total of 4 hydrogens and deleted the triple bond, which is equal to just drawing this. So you can see the alkyne is just gone. Take a look at another example. Here's a 3-hexyne. And if we treat that with the same conditions, hydrogen, palladium on carbon with, let's do ethanol this time. Let's draw the product. It can sometimes be a little bit easy to add or remove carbons, so let's number the carbons just to be sure. 1, 2, 3, 4, 5, 6. So our product should have 6 carbons, so it's just hexane. You can count 1, 2, 3, 4, 5, 6. So this reaction is a way to delete triple bonds, turn them into just single bonds. Not much more to say about this reaction other than there's no mechanism that you need to memorize or anything like that. Just this is it. Okay, but let's say you don't want to go all the way to an alkane. Let's say you want to turn an alkyne just into an alkene. We can do that too. This reaction 4 is called a partial hydrogenation. And this one is specifically with Lindlar's catalyst. We'll see there's going to be 2 variations of this reaction. This is with Lindlar's catalyst. Okay. And if we take that same alkyne, the 3-hexyne, and we treat it with very similar conditions, it's H2, but instead of using palladium on carbon, we just write Lindlar, which is a guy's name who invented this catalyst. I'll explain what the catalyst is in a moment. And ethanol, typically the solvent. And the product is going to be the cis-alkene. So it adds 2 hydrogens to the alkyne to make the cis-alkene. So syn addition of H2. So we're adding a hydrogen to each side of the alkyne. And we're adding it to the same side to get a cis-alkene. Now what's Lindlar's? It's funny. Oh, I misspelled it. It's Lindlar with an L in there. Lindlar's catalyst. It's just poisoned palladium. which is a fancy way of saying that it's palladium mixed with chalk. So palladium with calcium carbonate, which is just chalk. So literally all he did was take some palladium metal, stir it up with some chalk, like the same chalk you'd use to write on a chalkboard, and he sold that as Lindlar's catalyst. It turns out it works perfectly. The chalk causes the palladium to clump up, reducing surface area of the catalyst. And to me, I find this story quite motivating, because you take a look at this. Here's a guy who created something, made an innovation by taking something and making it worse. So if you ever feel bad, like you have nothing to contribute to the world, just think about Lindlar. Lindlar contributed to the world by making a great thing worse. So don't feel bad. Be like Lindlar. Okay? But his reaction is very important and very powerful in that it turns an alkyne into an alkene. Only way that would have been possible is by reducing the efficiency of that catalyst. Reaction 5 is very similar. It's a way to make transalkenes. So this is partial hydrogenation. With the Birch reduction. There's always some student on the exam that writes the Birch reduction. No, it is the Birch reduction, and watch your language. The reaction looks like this. You take an alkyne and you treat it with, it's a two-step process, and it's really easy to get it mixed up with something that's very similar. I'm going to warn you about that in a second. Step 1 is sodium metal. So I write sodium with a little dot, kind of like what we did lithium metal and magnesium metal. It's sodium metal, so little chunks of sodium metal. And the solvent is liquid ammonia. So it's done at very low temperature. So ammonia is the solvent, which is typically a gas at room temperature. So the fact that ammonia is being used as liquid solvent tells you that it's going to be at a very low temperature. And then step 2 is H2O. Again, don't worry about the mechanism for reactions 3, 4, and 5. And the product is going to be the transalkene. So it adds hydrogen and hydrogen across the alkyne, but it does so in an anti-addition fashion to give a transalkene. Okay, it's a lovely transalkene. Okay. This is also, if it's not called the Birch reduction, it's sometimes called the dissolving metal reduction. So if you ever hear that, that's what it's referring to. Dissolving metal reduction, because the sodium dissolves in the ammonia and it creates a beautiful blue color. So the blue color is thought to be solvated electrons. The reaction liberates electrons from the sodium metal, and which is then used to react with the alkyne in this reaction. So you can watch the sodium dissolve with the Birch reduction. Okay, just 2 more reactions left, and unfortunately, reactions 6 and 7 are probably the hardest reactions in this chapter. The good news is these reactions are very similar to things that we've seen already in the alkenes chapter, but there's a big problem. There's a twist. There's a difference in reactivity between alkynes and alkenes, and these reactions sort of reveal that. So before I even show you reactions 6 and 7, I need to tell you a fact. It's a fact about a property that certain molecules can undergo. I shouldn't say property, more of a process called tautomerization, which is a big word. I'll explain that. So these reactions are the addition of H and OH to alkynes. If you remember, we saw a few reactions that add H and OH, the elements of water, to alkenes. We saw the oxymercuration reduction, and we saw the hydroboration-oxidation. We are going to see the same reactions in the alkynes chapter in just a moment. Here's the concept. Okay, if you take an alkyne and you react it with a substance that adds water. Now, I'm just putting water in quotes. This does not actually work. You can't just add water to an alkyne. You have to add very special conditions to get you to add water to the alkyne. But the goal would be to create this substance, where you have an alkyne, now it's become an alkene, and you've added OH on one side and H on the other. That's a goal here. It turns out that this molecule is not stable. You can't have an alcohol directly attached to a double bond. It falls apart. This is called an enol. The ene stands for alkene, and ol stands for alcohol. So if you try and add water to an alkyne, you make an unstable enol because you end up with an OH group directly attached to a double bond. So what happens? If the enol is not stable, what does it do? It undergoes a process called tautomerization. Tautomerization is kind of like an equilibrium process. And it turns out that what ends up happening is this hydrogen on the alcohol moves onto this carbon over here, and the double bond moves back. The net result is that you get a ketone. So can you see that this hydrogen on the alcohol moved onto this carbon here? It's right here now. And that left the oxygen with nothing. And then the double bond moved up to create a CO double bond. And we call this the keto form. By the way, we'll look at an example of the keto form can actually be an aldehyde. We'll see that. That can happen if this R group happens to be an H. In other words, if this happens to be a terminal alkyne that you start with, the keto form can actually be an aldehyde. So this is an interesting thing. Notice what I'm saying here. If you take an alkyne and you add the elements of water, you don't get an alcohol like you did with alkenes. Instead, you get a ketone or an aldehyde. That's an important process because guess what that means? If you can take an alkyne and turn it into a ketone, well then guess what you're going to be able to do? All the ketone reactions. You're going to be able to do the Grignard addition. You're going to be able to do the sodium borohydride addition. Basically, your worst nightmare is going to come true with the turning an alkyne into a ketone. It's going to connect all of these reactions together. So let's take a look at reaction 6 on the next page. All right, reaction 6 is similar to the oxymercuration reduction. It has a slightly different name. It's called the acid and mercury catalyzed addition of H2O. Okay, and I'm not going to require you to know the mechanism of tautomerization. So you will have to learn it in 212. I'll let you learn it then. Okay, so if we take this alkyne, and the conditions are mercury sulfate, so HgSO4, H2O, and H2SO4. I know it's hard to keep it straight, so just look very carefully what it is. It's mercury sulfate, HgSO4, and then water, and then sulfuric acid all in one step. It's not step 1, it's not step 2. It's all just mixed together. So you could draw all of that on top of the arrow if you wanted. And then the product of that reaction is going to be as follows. First, this is Markovnikov. So it's going to add the alcohol to the more substituted side of our alkyne. In that case, the alcohol is added to the left, closer to the methyl group. But this isn't stable. This is an enol. So then it tautomerizes. Of course, you don't have to show this every time you show the reaction. I just want you to draw the final product for me. The tautomerization product is going to be where that alcohol turns into a ketone and the double bond disappears. So that's actually the product. It's just acetone. So notice it's just 3-carbon ketone, it's acetone. The regiochemistry is Markovnikov because the OH group was added to the more substituted side and the H went on the side with the most H's. Okay, let's take a look at reaction 7. The final reaction of the Alkynes chapter. And this is sort of analogous to the Hydroboration-oxidation, reaction 7 before I draw it out. It is actually called the Hydroboration-oxidation of alkynes. Okay. And let's take that same alkyne. It's a beautiful alkyne, so why not? And the conditions here are step 1, it's cyclohexylborane, which is CY2BH. CY stands for cyclohexane. I'll draw the structure down below in a second. And the solvent is typically THF. And step 2 is your favorite conditions, the H2O2 and NaOH, H2O. And let's see what happens here. In the first step, it actually adds boron to the least substituted side. So we get H here, and we get BCY2 added onto the less substituted side. Okay, that's the product of step 1. And then step 2 is the oxidation, which replaces the boron with an OH group. I'm putting these in brackets because none of these are isolated. They're unstable. And then step 2, we end up with the alcohol ultimately on the less substituted side, just like in the hydroboration-oxidation of alkenes, but this is an enol. So it tautomerizes. And so then the tautomerization product is where the OH turns just into a ketone or aldehyde. In this case, it turns into an aldehyde. So I'll even just draw the H that was there. Okay. So it takes a little bit of a second to see how this turns into this, but just follow my lead. The double bond moves upwards towards the oxygen to create a CO double bond, and the hydrogen moves onto that carbon over there, so that there's no carbocation at that position. Also, you wouldn't want the hydrogen still attached to our ketone, would we? So the hydrogen goes over there onto the other side, away from where it was. Okay, so take-home message here, reaction 6 turns a alkyne into a ketone, and reaction 7 turns an alkyne generally into an aldehyde. The regiochemistry here, non-Markovnikov. Since the hydrogen does not get added to the side with the most number of hydrogens. And I told you I'd show you the structure of cyclohexylborane. It looks like this. So you have boron, 1 hydrogen attached, and then there are 2 cyclohexanes attached. Okay. It turns out that this is a bulky borane. You can see it's quite large. And it's superior for alkynes. If you remember, for alkenes, we just used BH3. But for alkynes, we use cyclohexylborane. It works a lot better. Get better selectivity. Okay, so those are all the reactions of alkynes. We're almost done. There's just a couple more reactions left in this entire class. So thank you for keeping up with all these different reactions. Make flashcards, memorize what all these reactions do, look at the reaction summary to see which mechanisms you need to know. Hint, it's not really many of them for the alkynes chapter. Most of the time you don't need to know the mechanism for these guys, but definitely know what these transformations do, and definitely get some practice on this week's problem set. There's a lot of alkyne reactions on there. Okay, good luck. Talk to you soon. Bye for now.